Thank you for having me. This has been a fun conference. I'm Dan Björkegren at Brown University. This is a joint with Josh Blumenstock at UC Berkeley and Samsun Naïve, who's a fantastic grad student with me at Brown. An increasing number of decisions are made by algorithms. Algorithms decide what information you see on search or on social media, increasingly who receives a loan, who gets a job, and who's released from criminal justice, and on and on. And so these algorithms typically work by training a model. And so you might see some individual's behavior, some X's, and you link that to some desired outcome, some Y's, to try to make good decisions. So you look at historical correlations between these two variables and estimate some decision rule, Y hat of X. Now these types of models lead to two problems. The first is that once you've implemented this Y hat, if the stakes matter, then individuals may game their behavior. And so those X's that you put into your model may actually be a function of the model that you use. And the second issue is that there's concern about these decisions being made in black boxes. So on this first concern about manipulation, firms spend billions of dollars trying to manipulate where they appear on Google and other search engine results. And pretty much any algorithm you can think of, if you Google it, you can find some tricks to how to manipulate it. Insurers in China tried to introduce health insurance plans that gave you a discount for achieving a certain step count. And engineers came up with a new type of cradle that rocks the phone in order to manipulate the step count. And so some of these examples seem kind of fun, but manipulated algorithms can make decisions that may be arbitrarily poor or unsafe. There are examples of lending portfolios that initially seem to be fine, but become swamped with fraud as soon as actors figure out how to manipulate the credit scoring rules. There's concern about social networks being overrun with content that's engineered. And there's evidence that you can easily trick self-driving cars into crashing, for example, by slightly modifying stop signs. The second concern is that as important decisions are being made by these algorithms, that bias may be embedded into these systems. And so there's been an increasing push for a right to explanation. The GDPR in the European Union gives individuals some right to be told what the logic involved in automated decision-making is. But the more transparent you are about what goes on inside that black box, the easier these systems are to manipulate. And under current practice of training these rules, transparency may undermine the use of machine learning altogether because it exacerbates these systematic risks. This project asked the question of whether we can address these two problems simultaneously. We build equilibrium decision rules that continue to function even when they're fully transparent and even when they face manipulation. It has two parts. So first, we develop a theory, which is a method to solve for these equilibrium decision rules, given information about the cost of manipulation. And second, an empirical exercise in a field experiment in Kenya, where we both estimate these costs of manipulating behaviors and then test the value of our strategy robust algorithm. So the field experiment just finished a couple months ago, and so this is all pretty fresh, and any feedback is very much welcome. This problem of manipulation is not new. You can think about classic literature on the Lucas critique or Goodhart's law, that as soon as you try to take advantage of some correlation in data, agents may manipulate it and it may cease to be predictive. It also relates to literature in mechanism design and contract theory. And the closest two papers are Frankel and Kartik's paper showing that when individuals can game behavior, but that ability to game is heterogeneous, that can muddle the information in a market. And also Ian Ball's paper on scoring strategic agents, which ends up with a similar model to ours, and he's able to show that the existence of equilibrium in that context. It's also related to the problem of taxation, where once you tax something, individuals will try to avoid being taxed by changing their behavior. There's also literature in computer science that thinks about strategic classification, how people might manipulate their behavior in theory, and also in adversarial machine learning when people particularly want to undermine a system. Our contribution here is to develop a method to estimate these equilibrium decision rules with real data and a real world stress test. There have been two common ways to think about this problem and that have been implemented. So the first that you might think it would be natural as an economist might be to say, well, let's use a theory-based or a kind of raw structural approach where we just don't allow our decision rules to use features that can be manipulated. And that might be fine for kind of traditional settings where you don't have that many features altogether. But if you're looking at modern data sets that have thousands and thousands of features, it doesn't make much progress. And additionally, you might be throwing away a lot of predictive value because most features can be manipulated at some cost. So what's actually used in practice and what we're calling the industry approach is to keep decision rules secret so that it's harder to manipulate them. And this is sometimes referred to as security through obscurity. And so you might see some observed data and then train your model. Now, even if you try to keep your decision rule secret, it's possible to reverse engineer it. And if the stakes are high enough, that typically happens. So in these implementations, typically these firms have to retrain the model. And so once they've implemented the model, the other side of the market will figure out flaws in it. And then they'll typically retrain that model or refresh it over and over. Now, this has two problems. So the first is during this process, you're exposed to systematic risk. So it could be making extremely bad decisions at any point in time, and you're not really sure whether your system is gameable or whether you're susceptible to fraud or other problems. And the second is that it's not actually clear whether you'll end up in an equilibrium altogether or whether that equilibrium will be desirable if you do. Our approach is recognizing that this back and forth looks like a process of equilibration. Instead of doing it in the real world where it's costly and risky, we could do that equilibration in a model. And so what happens if we solve for the equilibrium decision rule y star that's optimal, anticipating that people will respond against it? So we'll flesh this out by going through a simple model, and we're going to kind of focus on one particular application here, which is a policymaker that wants to give out rewards to individuals. So you can think of this as like a poverty targeting application where we want to find who people who are poor are or have some other desired tag. So we have a policymaker who wants to give each individual I in this economy some reward yi based on some fixed type that they have. So this is x underbar I. And so here, this could represent the function mapping that type to the desired payment. But this policymaker doesn't actually see these fixed types. They see behavior. So they see some behavior xi, and so they implement some decision rule y hat of xi, which it can be a linear function of the behavior that they observe. Now, I cares about the decision that they get. So I gets utility from this y hat I, but they incur some cost if their behavior deviates from their underlying type. So, and this is the cost of manipulating their behavior. And we model that cost as a quadratic, just to keep things simple. And that cost can be different in two ways. There can be some individuals that find it easy to game. These may be people who are very savvy or have a lot of time to figure things out. And then also some indicators may be easy to game and some may be harder. We'll be talking about an application of digital credit where the decision of whether you get a loan will depend on how you use your cell phone. And it turns out that it's fairly easy to manipulate your outgoing calls. You just call a bunch of people, but harder to manipulate incoming calls because it's hard to get people to call you. And so those will be factored in this matrix. And there can also be cross costs. So it could be hard to manipulate some things together or easy to manipulate some things together. So given that model, if I knows this decision rule of how they'll be judged and how they'll get rewards, then they're going to choose a behavior according to this function. So their behavior is going to equal their underlying type. But when this beta rule is not 0, when there's some incentive to change their behavior, they're going to shift their behavior in the direction that they're incentivized to, but downweighted by this cost of manipulation. And so then this leads us to a decision rule. And so if you address this problem in a kind of standard way, which would be the case in using OLS or lasso or any other standard machine learning method, you would assume that there's no manipulation, that whatever you see in your baseline data, the x's, are going to be fixed when you actually implement your decision rule. And so if we ran OLS, this is the loss function we would minimize. Now, our approach is going to be different because we're going to assume that those x's are actually going to change. And so our strategy robust decision rule anticipates this manipulation. And so these x's are now a function of the betas. The more incentive we put on a certain behavior, the more we'll see of that behavior. And our model tells us exactly how those relate. And so this is kind of the central insight of the model, that we get this kind of simple estimator here. It ends up being nonlinear least squares for this linear decision rule. And you can solve that. And so let's look at an example. So now imagine this might be the case where you have outgoing calls and incoming calls, and you can use those are correlated with your creditworthiness, for example. And it may be that outgoing calls just happen to have a higher coefficient if you ran the baseline regression. So they seem to have like a stronger relationship to desired repayment. If you ran OLS, you would just pick up that relationship that you saw in the baseline data. And those estimates you would get would not depend on how easy it is to manipulate these behaviors. And that prediction can perform just fine when it's very costly to manipulate these things. But if it becomes easy to manipulate these things, then this can become extremely, can perform extremely poorly. And so let's think about this case where at baseline, this x1 has this higher predictive performance, and x2 has a lower predictive performance, but x1 is actually much easier to manipulate. If you thought you could solve that problem with lasso, it turns out lasso does exactly the wrong thing. So lasso is going to penalize them both based on how predictive they were in the data that you saw, and you didn't see any manipulation in that initial data. And so it's actually going to keep the indicator that you don't want in the regression. It's going to keep x1 in the regression, even though you'd rather switch to x2, because x2 is going to be manipulated. So our estimator is going to kind of smoothly account for this. If it's really costly to manipulate behavior, then it's going to approach OLS. But as it becomes easier to manipulate behavior, it's going to shift weight from this indicator that seems like it might be good, but would be very manipulated as soon as you used it, to the one that actually is harder to manipulate. So there's a few more simulations in the paper, but we also ran an experiment to test this in the real world. And our goals here were to create an environment where some desirable resources are allocated based on behavior. In this environment, we're going to estimate the main parameters here, the cost of manipulating different behavior, an individual's types, and their ease of manipulating. And then we're going to test our two models and also use this to calculate the equilibrium cost of transparency. So how much performance do you give up to make your models transparent? And we're going to do this experiment in a setting that mimics digital credit in Kenya. So there are about 2 billion people who lack access to formal financial services, but many of these individuals have cell phones. And so about 10 years ago, I came up with an idea to use how a person uses their cell phone to predict whether they'd repay a loan. And it turns out that idea has taken off. There's a number of providers in Kenya and around the world that now offer digital credit. In Kenya, 27% of the adult population has taken out a digital credit loan. Like other contexts. And so typically you install an app on your phone and it downloads your data and decides whether you're creditworthy and then gives you a loan directly via mobile money. And like other settings where algorithms are being used to make decisions, this is subject to the same two problems that we started off with. Individuals have figured out how to game these systems and take out money that they intend never to repay. And so this has caused a lot of issues for the balance sheets of these firms and raised questions about sustainability in some contexts. And you also see people discussing how these rules work online. And at the same time, regulators are confronting the issue that their populations are being, some people in their country are being denied credit for reasons that are not disclosed. And so regulators want there to be more transparency in why people are approved or denied. Of course, transparency could make these issues of manipulation worse. So to mimic this setting, we built a new smartphone app together with the Busara Center for Behavioral Economics in Nairobi, and it has a few key features. So the first is that it collects the same digital data, the same behavioral data that the digital credit app would. And to be clear, we were very clear with participants about what data we'd be collecting. It was anonymized, so we didn't have access to it, to the identifiers. And it's still sensitive information, and so we made sure to be clear with participants about what it would all entail. In the end, our participants trusted the Busara Center, and we're pretty excited about joining the study. The second feature is that it also provides rewards to users based on their behavior. So each week you would get some challenge, and the challenge might say you don't need to do anything, or the challenge might say you will get paid, for example, for using sports apps. Or the challenge may be more complex. It may be asking you to act like a certain type of person. We wanted to mimic digital credit, but it was going to be hard to actually give out people loans and assess creditworthiness. So instead, we used other characteristics like income level, education, marital status, etc. And so you might receive a challenge like this that says you'll get paid if this app guesses that you're a high income user based on your calls, texts, and app usage. And you might be told no information. Or some individuals received a transparent description of this algorithm. So they were told exactly what the decision rule is and given a tool to help them calculate their earnings. So if you just look at individuals' baseline behavior, consistent with other work in this literature, we found that how you use your phone is predictive of what type of a person you are. Here, the relationship is not super strong, but we at least find some predictive performance of monthly income, marital status, Raven's matrices, and popularity. And so, but we also find that these behaviors are manipulable. So if we send people a challenge that says that they'll receive a certain amount of money for each missed call they receive that week, then we see them receive more missed calls. We also see them change a couple other behaviors. So they tend to call more people and send a few more text messages. And so we do this, we send these challenges randomized in a randomized manner for a whole number of behaviors. And then we see responses on many of them, suggesting that when you are incentivized to do something, you do it. And we're going to use this information to estimate the cost, how costly it is to manipulate these different dimensions of behavior. So from before, our estimator of a robust decision rule requires this cost matrix and also information about individuals' types and their gaming ability. And we're going to jointly estimate these with GMM. And there's some more technical details in the paper, which you're welcome to read. We're going to end up regularizing these decision rules down to 3 coefficients just to make things easy for individuals to interpret. And there's also some regularization on the cost matrix itself. And so what we see is that there are different costs to manipulating these different behaviors. And one pattern you see is that it's easier to manipulate the behaviors that you yourself have control over, sending texts or making calls, rather than the ones that require other people to do things, like receiving calls or texts. And you also see a couple other patterns, things that are complex tend to be harder to manipulate, and so on. And then we actually implement decision rules, and we try to see if you just ran OLS, or in this case lasso, to try to estimate what are the factors that correlate with income, what you see is that people who are higher income tend to place more outgoing calls, they receive more SMS, and they send slightly fewer SMS. But if you saw that descriptive correlation and thought, well, I'm going to try to figure out who's high income based on this and give a reward to them, you actually find that they change their behavior. If you just tell people that you'll receive a reward for being thought to be a high income earner, then you see that the movement is kind of noisy. In some cases, it's in the right direction. In other cases, it's not. If you also tell them exactly how they will be assessed and this decision rule, you see it's also still kind of noisy, but you see them move more in the correct direction. So they place more outgoing calls. And so the naive model places exactly those weights on it, just looking at the descriptive data. A robust model adjusts these coefficients, and in particular is going to shift weight to indicators that are harder to manipulate. And so it zeroes out incoming SMS and replaces it with evening SMS, and also shrinks down coefficients that are easier to manipulate. We next assess the performance of this, and it turns out that the naive model performs better if there's no manipulation. So at baseline, if you just tried to optimize it, it looks like that performs better. But in the case where we actually show people how this works and people game it, then ours performs better. And so you can think of our model, so our model generates linear decision rules. You can think of it as another class of linear model, where OLS maximizes fit within the sample that you observe. Instrumental variable says, well, let's give up some of this fit that we have in the in-sample that we observe in order to get a causal estimate of a coefficient. Lasso will say, let's give up some fit in sample to do better on another sample drawn from the same distribution. Our method is a new category here where we say, let's give up some fit in sample, as on this top row here, to do better in the counterfactual, where our decision rule is transparent and people manipulate against it. And we also see that our robust model is also more stable. It's less impacted by strategic behavior. So this is great. This means that we might be able to assess some progress and make better decisions that are less exposed to the systematic risk. But it also gives us a tool to assess these proposals for more transparency in machine learning, where if a policymaker says, let's move to make tech firms release exactly how their search engine rankings work or how Facebook prioritization works, then often these firms will push back and say, you know, if we did that, these would be gamed and completely undermined, and perhaps our service wouldn't work at all. And so this is a question that we're able to answer here. And so if you just take this naive model, the lasso model, we can compute the prediction error. And because we've randomized some people into opaque treatments and some into transparent, we can estimate this cost of transparency. And in this status quo, we find that moving from opacity to transparency costs about 93 cents in prediction error, or the equivalent of 25% of performance. But in practice, you would probably want to adjust your decision rule under transparency. And our approach allows you to show how that might happen. And so what we find is that if you instead move to our decision rule under transparency, then it only adds about 31 cents of cost in performance, or it reduces it down to 8.2%. And so this gives you some sense of how costly is it if we move to a new equilibrium where transparency is the norm. And just one note about that. So the way that this table is constructed, we actually told some people exactly what the decision rule was. In practice, if you went to Google and said, we're going to release exactly what your algorithm does to a small subset of people, those people would probably tell other people, and eventually everyone would know. And so in some cases, it's not practical to run this exact experiment where you tell people exactly the decision rules. And in those scenarios, our model actually allows you to assess the same quantity without actually revealing the decision rule. So you can estimate in our model what the cost of transparency is, and then predict how much a rule would be manipulated, and also estimate what the best rule would be in equilibrium, even without telling people what is actually in that model. And so we think that's a pretty promising direction so that society can start to think about the costs and the benefits of moving to transparency. So just to wrap up, so this is a model that introduces a theoretical contribution, which is a new method that allows you to solve for equilibrium decision rules, which are robust to manipulation, even when they're fully transparent. And second, an empirical application. And we find that in our field experiment that these strategy robust estimators can perform better when people manipulate their behavior. And generally we think of this, so this setting is a bit simple, but we think of it as a new framework for thinking about prediction in the face of manipulation. One simple extension to start with would be to think about other ways to estimate costs. Here we did this kind of big experiment, but we have some evidence that if you ask experts to predict these costs, that they have there's some useful content in that. And there's a couple other approaches that we're trying out. And we also think that this can be extended. Obviously, this is a linear model, but we think that this could be extended to nonlinear models that are more common in other machine learning applications. Also more nuanced beliefs, like what if people only have partial transparency about how these things work, and more nuanced cost structures. Like what if there's a fixed cost of learning how to manipulate something before you actually start. And kind of taking a further step back from that, I think generally it shows a new way for economics to interface with machine learning, and that is by embedding our models of behavior within machine learning estimators, we can start to think about how to solve this Lucas critique in real settings. And so in that sense, it provides a sort of machine learning interpretation of the Lucas critique. And we're very excited about the potential for that to make a huge difference in this. And it's either as a way for economics to contribute. So that's all I have.